A frozen world at the edge of our solar system holds secrets that defy explanation. This is Eris, a dwarf planet more massive than Pluto, reigning in the dark expanse of the Kuiper Belt. It was discovered nearly 2 decades ago, yet it remains one of the most profound cosmic puzzles we have ever encountered. Today, we are embarking on a journey through 25 of its most baffling enigmas, mysteries that challenge the very foundations of what we know about our own celestial neighborhood. By the end, you will see our solar system not as a finished map, but as a frontier still whispering with unanswered questions. How can a world so far from the sun have a surface brighter than fresh snow? What hidden force could possibly sculpt its wildly looping path through space? The answers are stranger than we ever imagined. What does it mean when a single distant dot of light forces us to rewrite the rules? That brilliant shine was the first clue something was profoundly different. When Eris was first spotted, its reflectivity, what astronomers call albedo, was measured as astonishingly high. It gleams, reflecting back nearly all the sunlight that touches it. This immediately set it apart from most other known Kuiper Belt objects, which are typically dark and charcoal-colored. The initial, most logical assumption was that its surface must be dominated by volatile ices, much like its cousin Pluto. We expected vast plains of frozen nitrogen, perhaps with a sprinkling of methane and carbon monoxide, creating a bright, mirror-like shell over a rocky core. It seemed a perfect, if distant, twin, but the deeper we looked, the less that simple picture held together. Spectral analysis, which breaks down the light bouncing off Eris into a chemical fingerprint, began to tell a more complex and contradictory story. Yes, there are clear signs of methane ice, but the data suggests this methane isn't pure and crystalline like we might find on Pluto. Instead, it appears to be heavily processed, possibly mixed with darker, complex organic compounds called tholins. These are the same substances that give Pluto its reddish-brown hues and color Saturn's moon Titan. Their presence on Eris implies that its surface chemistry has been active over eons, with methane being broken apart by the feeble sunlight and cosmic radiation, then recombining into these more complex reddish gunk. Yet, Eris remains dazzlingly bright. This creates a paradox. How can a surface be both coated in dark, reddish tholins and still be one of the shiniest objects we know of in the outer solar system? One compelling theory is that Eris's surface is a dynamic, ever-changing landscape. The extreme cold and vast distance from the sun mean any geological activity would be incredibly slow by our standards, but it might still be happening. Some scientists propose a process called sublimation-driven renewal. Imagine the faint warmth of the distant sun over millions of years, causing patches of volatile methane or nitrogen ice to turn directly from a solid into a gas. This gentle outgassing could carry away darker dust and tholins, constantly refreshing the surface with a bright, new layer of frost. It would be a self-cleaning cycle on a geological timescale, perpetually maintaining that brilliant facade. If true, it means Eris is not a dead, static ball of ice, but a world with a slow, hidden heartbeat of activity. The problem is we lack the definitive proof. Without a close-up visit from a spacecraft, our view is a blurry pixel. We are trying to decipher the intricate details of a fresco by looking at it through a keyhole from a mile away. The true nature of that glowing surface remains our first and perhaps most fundamental mystery. That brilliant, contradictory surface is only the outer shell of a deeper puzzle. To truly understand Eris, we must look beneath its icy facade, and what we find there defies expectations. From careful measurements of its orbit and the motion of its moon Dysnomia, astronomers calculated Eris's mass with remarkable precision. Combined with estimates of its size, this revealed a startling fact. Eris is incredibly dense. For an object in the frigid Kuiper Belt, expected to be a fluffy mixture of ice and rock, its density is surprisingly high. This number tells a story of compression and composition. It strongly suggests that a significant portion of Eris's interior is not ice at all, but rock and metal. The leading theory is that Eris is a differentiated world, meaning its materials have separated over time. Imagine a snowball mixed with dirt and gravel. If you could squeeze it with immense force and warmth, the heavy rocks would sink to the center while the lighter ice rose to the surface. Scientists believe this is exactly what happened inside Eris billions of years ago. It likely possesses a substantial rocky core, perhaps as large as the planet Mercury's, enveloped by a thick mantle of water ice and other frozen volatiles. This structure alone makes it a geological oddity so far from the Sun, but the implications grow even stranger from there. If Eris has a rocky core insulated by an icy shell, a tantalizing question emerges. Could there be liquid water hidden deep below that frozen crust? The idea of a subsurface ocean on a world over 4 times farther from the Sun than Pluto seems at first laughable. The outer solar system is a deep freeze, yet we now suspect Pluto itself may harbor a global ocean beneath its heart-shaped glacier. The heat required to keep water liquid there isn't from the Sun, but from within. Radioactive elements decaying in Pluto's rocky core, combined with the insulating power of a thick ice shell, might provide just enough warmth. For Eris, however, the math becomes far more challenging. It is smaller than Pluto, which means its internal heat from formation and radioactive decay should have dissipated faster. Its ice shell is likely thicker and colder. Every thermal model we have struggles to explain how any residual heat could persist for billions of years to maintain a liquid layer, but the density data keeps the door open. Perhaps Eris experienced a more violent formation, with collisions generating extra initial heat that was trapped more efficiently. Maybe its interior chemistry or the unusual properties of high-pressure ices create unexpected insulation. The possibility, however slim, forces us to reconsider what it means for a world to be alive. Geological activity isn't always volcanoes and geysers. It can be the slow, hidden churn of a buried sea, the silent flexing of an ice shell over a liquid heart. If Eris holds such an ocean, it would be one of the most isolated bodies of water in existence, a dark, pressurized abyss that has never seen sunlight, existing in perpetual silence at the edge of everything. This transforms Eris from a simple ice ball into a potential sanctuary, a locked vault that might, against all odds, cradle the ingredients for chemistry we dare not yet name. This hidden ocean, if it exists, would be locked beneath a crust of unimaginable cold, on a world whose very journey through space is a story of chaos. Eris does not follow a polite, circular path around the Sun like the planets. Its orbit is a dramatic, elongated ellipse, a wild loop that takes it on a 558-year journey from a point 38 times Earth's distance from the Sun all the way out to a staggering 97 times that distance. For perspective, at its closest, it is still billions of miles beyond Neptune. At its farthest, it ventures into the deepest, darkest reaches of the scattered disk, a population of icy objects with wildly tilted and stretched orbits. This path is not just elongated, it is also sharply tilted, inclined by a steep 44 degrees compared to the flat plane where the planets orbit. Eris is not merely a resident of the outer solar system, it is a cosmic drifter, a refugee on an extreme and lonely highway. The question of how it got there is one of the great detective stories of planetary science. The most widely accepted theory points an accusing finger at Neptune. In the solar system's violent youth, the giant planets are thought to have migrated, shuffling their positions and scattering countless icy bodies in all directions. Eris, according to this model, was once a member of the primordial Kuiper Belt, a closer neighbor to Neptune. A series of gravitational nudges from the ice giant, like a cosmic slingshot, could have flung it outward, pumping up its orbit's eccentricity and tilt, casting it into the scattered disk where it resides today. This story fits neatly with our understanding of Neptune's influence on other objects like Pluto. Yet for Eris, some astronomers wonder if the story is quite that simple. Its orbit is so extreme that it pushes the limits of what Neptune's gravity alone could easily explain. This has led to a more speculative but thrilling alternative. Could Eris's path be evidence of a ghost, a gravitational signature from a past encounter with an unseen world? Some dynamical models suggest that the peculiar orbits of Eris and several other distant objects could be best explained by the gentle, persistent tug of a large, undiscovered planet lurking far beyond Neptune, a hypothetical world often called Planet 9. In this scenario, Eris's orbit is not just a relic of ancient chaos, but a modern-day clue, a breadcrumb left in the darkness pointing toward something massive we have yet to find. Whether shaped by a known giant or an unknown one, Eris's journey tells us the outer solar system was not a quiet nursery. It was a shooting gallery, a place of gravitational upheaval where worlds were tossed about like dice. Eris, in its solitary, looping dance, is a permanent record of that epoch of turmoil, a frozen testament to a time when the solar system was rearranging its own furniture with catastrophic force. The chaotic journey of Eris is mirrored in the story of its solitary companion. Orbiting this distant dwarf planet is Dysnomia, a moon that is itself a profound mystery. Its very existence speaks of a cataclysmic past. Dysnomia is not a small, captured asteroid. It is remarkably large for a moon of a dwarf planet, estimated to be about 1/8 the diameter of Eris itself. This size ratio is strikingly similar to that of Earth and our own moon. That similarity is the key clue. Just as scientists believe our moon was born from a colossal impact between a young Earth and a Mars-sized object, Dysnomia likely formed from a titanic collision in the early Kuiper Belt. Billions of years ago, a primordial Eris may have been struck by another large icy body. The incredible force of that impact would have vaporized and shattered both worlds, hurling a massive cloud of debris into orbit around what remained of Eris. Over time, that debris coalesced under its own gravity to form Dysnomia. This means the moon is not a stranger that wandered by, but a piece of Eris itself, a child born from unimaginable violence in the deep freeze of space. The relationship between this parent and child is now one of perfect, silent harmony. Eris and Dysnomia are tidally locked to each other. This is a precise gravitational dance where each body always shows the same face to the other, just as our moon always shows the same face to Earth. From the surface of Eris, Dysnomia would hang motionless in the sky, a permanent fixture among the stars. From Dysnomia, Eris would loom, forever fixed. This locking didn't happen overnight. It is the end result of eons of gravitational interaction, a tug of war that slowly break their rotations until they reach this stable, synchronized state. The time it took to achieve this lock is a secret telltale. It depends critically on the internal structure of both bodies. If Eris or Dysnomia were perfectly rigid, solid balls of rock and ice, this process would have taken much longer. The fact that they achieved this lock suggests at least one of them, and likely both, are or were somewhat flexible and deformable. This supports the idea that Eris has a differentiated interior with distinct layers that can flex under tidal forces, and that Dysnomia itself may not be a simple, homogeneous lump of ice. Their locked dance is a fossilized record of their internal squishiness. Yet, for all we can infer, Dysnomia remains a silhouette. We know its approximate size and orbit, but its surface properties, its color, its composition are complete unknowns. Is it covered in the same bright, processed ice as Eris, or is it darker, revealing a different layer of material blasted out from the impact? Its surface could be a pristine sample of Eris's ancient interior, material that was buried deep and untouched for eons before being excavated in that giant impact. Analyzing Dysnomia would be like taking a core sample of Eris without having to dig. Every crater, every chemical signature on that distant moon could tell us what Eris is made of beneath its shiny shell, and what exactly smashed into it so long ago. For now, it is a blank page in a story we have only begun to read, a silent witness to a collision that shaped two worlds at the edge of everything. Dysnomia's silent vigil hints at a past of violent change, but the surface of Eris itself suggests an ongoing, hidden process. That incredible brightness, its albedo, is a glaring anomaly. This distant world reflects over 95% of the sunlight that reaches it, making it one of the shiniest objects we know of, its surface rivaling the reflective power of freshly fallen snow on Earth. For a place so far from the sun, a frozen graveyard where everything should be dark and inert, this is utterly perplexing. A surface that bright cannot stay that way for billions of years. Cosmic dust should slowly rain down, darkening it. Radiation from space should bake and redden the ices, creating those complex tholins we detect, yet Eris gleams. This forces a radical conclusion. Its surface is being actively maintained. It is being cleaned, repainted, or resurfaced by some hidden mechanism. The leading suspect is a process of volatile transport, a slow-motion seasonal cycle driven by the faint warmth of the sun. Here is how it might work. As Eris travels along its wildly elongated orbit, its distance from the sun changes dramatically over centuries. When it is at its closest approach, the feeble sunlight, though still incredibly weak, provides just enough energy to warm specific ices on the surface, like nitrogen or methane. These super-volatile ices don't melt, they sublimate, turning directly from a solid into a thin, temporary atmosphere. This gentle outgassing would carry away the accumulated dark dust and reddish tholins, lifting them off the surface. Then, as Eris swings back out to the frigid depths of its orbit, this tenuous atmosphere collapses. The gases refreeze, not randomly, but as a fine, bright, pristine frost that snows back down uniformly, coating the entire world in a new layer of brilliant white. It is a self-cleaning cycle on a geological clock, a world that exhales a ghostly breath and then inhales it back as a blanket of frost. This would make Eris a dynamic world with seasons, but seasons that last not months, but decades or even centuries. The concept of cryovolcanism adds another layer of intrigue. Could there be internal heat, perhaps from that dense rocky core or from the decay of radioactive elements that is still slowly leaking out? This might not create fiery lava, but a sluggish, cold eruption of water ice mixed with ammonia or other antifreeze compounds. If such a slushy mix were to ooze onto the surface, it would immediately freeze into a smooth, bright plane, again refreshing the albedo. The problem is evidence. We see the dazzling result, but from our distant vantage point, we cannot watch the process in action. We cannot see the plumes of gas or the flow of cryomagma. We are left with a snapshot of a brilliantly white world and must deduce the movie that created it. This transforms Eris from a static ice sculpture into something potentially alive with slow, majestic change. It suggests that even in the deepest cold, at the very frontier of our solar system, worlds are not simply frozen in time. They breathe, they renew themselves, and they guard their secrets beneath a cloak of freshly fallen ice. The brilliant frost covering Eris could be the breath of a ghost. The possibility of a temporary atmosphere is one of the most heated debates surrounding this distant world. For an atmosphere to exist so far from the sun, the physics are pushed to their absolute limit. Gravity is the first requirement, and Eris, with its substantial mass, has enough to hold onto gases, provided they are cold enough to move slowly. But the real challenge is the sun's energy. At Eris's average distance, sunlight is over 1,000 times weaker than what we experience on Earth. This feeble warmth is barely enough to coax the most volatile ices, like nitrogen or methane, directly from a solid into a gas, a process called sublimation. This means any atmosphere wouldn't be permanent like Earth's, but a fleeting, seasonal phenomenon, entirely dependent on the world's temperature. To solve this mystery, astronomers have employed a clever celestial trick called a stellar occultation. They wait for Eris to pass directly in front of a distant star. By watching how the star's light dims and flickers as it is blocked by Eris and any potential atmosphere, scientists can measure the dwarf planet's size with incredible precision and detect the subtle signature of gases. The results, however, have been maddeningly contradictory. Some occultation events have shown a sharp, clean cutoff of the starlight, suggesting Eris possesses no detectable atmosphere at all, just a bare, frozen surface meeting the vacuum of space. Other observations, however, have hinted at a faint, gradual dimming of the star just before and after Eris itself blocked it. This soft edge is the telltale sign of a thin, hazy envelope of gas, perhaps only a few billionths the pressure of Earth's air at sea level. This could be a whisper-thin shroud of nitrogen or methane, clinging to the world only during the warmest part of its long orbit. The implications of this yes or no answer are profound. If Eris has even a transient atmosphere, it becomes a much more active world. This thin gas would act as a blanket, however slight, trapping minuscule amounts of heat and influencing surface temperatures in complex ways. It would be the engine for the very resurfacing cycle we suspect, allowing ices to sublimate, carry away dark dust, and then refreeze elsewhere as bright frost. Wind, unimaginably gentle by our standards, might stir fine particles across the landscape over millennia. Frost could migrate from warmer, sun-facing patches to permanently shadowed craters, creating hidden cold traps. If no atmosphere exists, the story changes completely. Eris would be a stark, airless tomb. Any surface renewal would have to be driven internally by cryovolcanism or tectonic shifts, making its brilliant shine even more difficult to explain. The presence or absence of this ghostly breath determines whether Eris is a world with seasons and weather, or a silent, static monument. For now, the data whispers two different stories, and we are left waiting for another star to wink out behind that distant point of light, hoping for a clearer signal from the dark. The debate over Eris's atmosphere is a whisper compared to the earthquake it caused in our understanding of the solar system. The discovery of this distant world ignited a controversy that reached far beyond astronomy, shaking textbooks and public perception alike. In 2005, when the team led by Mike Brown first announced the object then known as 2003 UB313, they made a startling preliminary claim. Based on its incredible brightness and an assumed surface reflectivity, their initial calculations suggested it was larger than Pluto. The media seized on this instantly. Headlines around the world declared the discovery of a 10th planet, a new member of our cosmic family that was bigger than the beloved 9th. This was not just a new object, it was a direct challenge to Pluto's status. The astronomical community was thrown into turmoil. For decades, Pluto had been an oddball, a small, icy world with a tilted orbit that never quite fit with the other 8 planets. Now here was something seemingly larger, farther out, and undoubtedly more massive, waiting in the wings. If Pluto was a planet, then Eris certainly had to be one too. And if both were planets, then what about the other similar-sized objects we were beginning to find in the Kuiper Belt? Would we soon have 50 planets or 100? The crisis came to a head in 2006 at the International Astronomical Union's General Assembly in Prague. Astronomers were forced to do something they rarely do, define the word planet formally. After intense and passionate debate, they established 3 criteria. A planet must orbit the Sun. It must be massive enough for its own gravity to pull it into a round shape, and it must have cleared the neighborhood around its orbit. Pluto, and by extension Eris, failed the 3rd test spectacularly. They share their orbital space with thousands of other icy bodies. In a historic vote, Pluto was reclassified as a dwarf planet, a new category created that day. Eris, the instigator, was immediately placed into the same category. The public reaction was one of shock and even mourning. Pluto had been demoted, but the story of Eris's size had a final, ironic twist. Those initial size estimates were based on a guess about its reflectivity. As better observations came in, including those precise stellar occultations, astronomers got a true measurement. Eris's diameter was finally pinned down to about 2,326 kilometers. Pluto's, measured by the New Horizons spacecraft, is about 2,376 kilometers. By a razor-thin margin, Eris is actually slightly smaller in physical width, yet it remains more massive. This is the crucial detail. Eris packs more material into a slightly smaller volume, confirming its astonishing density. So, while it did not dethrone Pluto in size as first believed, its mere existence and its greater mass were the catalysts that forced us to rethink our cosmic map. Eris, the world that sparked a revolution, is forever linked to Pluto not as a usurper, but as a mirror, reflecting our own evolving understanding of what it means to be a planet at the edge of the dark. That gleaming surface is more than just bright, it is suspiciously smooth. If Eris is as ancient as the rest of the solar system, its icy skin should be a battered landscape, pockmarked with the scars of countless collisions over 4.5 billion years. The Moon, Mercury, even Pluto show this violent history written in craters. Yet, from what we can discern across the vast distance, Eris does not. Its high reflectivity suggests a surface that is not only clean but young, geologically speaking. This is the mystery of the missing craters. It points to a world that is actively erasing its own history, a place where some powerful process is constantly repaving the frozen ground, wiping away the evidence of ancient impacts as fast as they appear. The implication is staggering. Eris is not dead. Something beneath its icy shell is stirring, but what force in that profound cold could possibly be at work? One compelling possibility is cryovolcanism. Forget fiery molten rock. Think instead of a slow, cold eruption. Imagine a slushy mixture of water ice, perhaps laced with ammonia or salts acting as a powerful antifreeze. Deep within Eris, residual heat from its rocky core or from the decay of radioactive elements might keep this icy sludge just warm enough to remain pliable. Under pressure, this cryomagma could find a weakness in the overlying crust and ooze onto the surface. As it spreads, it would flow like glacial syrup covering older, cratered terrain with a smooth, bright new layer that freezes solid in the deep cold. This would be geology in extreme slow motion, a single eruption possibly taking thousands of years to cover a vast plain, but the result would be a pristine, unblemished surface. Another, even more exotic mechanism is convective overturning. Eris's thick mantle of water ice is not necessarily a static block. Over immense timescales, even solid ice can behave like a fluid slowly churning. Heat from the interior makes deeper ice slightly warmer and less dense. This warmer ice can slowly rise in great, sluggish plumes while the colder surface ice sinks. Think of a pot of thick pudding on a very low heat, bubbling with a patience that spans millennia. This constant internal recycling would bring fresh material from the interior up to the surface, while dragging the old, cratered crust down to be melted and reprocessed. The entire outer shell could be turning over like a cosmic conveyor belt, perpetually presenting a new face to the stars. This process would efficiently erase craters and could also explain the uniform brightness as it constantly exposes unweathered ice. A third, more catastrophic idea is a global resurfacing event. Perhaps Eris experiences episodic cataclysms. A buildup of internal heat over hundreds of millions of years might suddenly find a release, not in localized volcanoes, but in a planet-wide shattering of the ice shell. The entire surface could fracture, with vast sections sinking as warm slush floods up from below, creating a global ocean of slurry that then refreezes into a smooth, new crust. This would be a rebirth, a total renovation that leaves the world looking brand new, with every ancient crater and valley filled in and forgotten. All these theories, however, circle back to one immense puzzle, the heat source. What could possibly keep Eris warm enough for such activity so far from the Sun, so long after its formation? Radioactive decay in its rocky core is the standard answer, but for a world of Eris's size, that heat should have faded into insignificance eons ago. Could its dense interior have an unusual concentration of radioactive elements? Did the colossal impact that created Dysnomia deliver a surge of tidal energy that somehow got trapped? Or is there another, more subtle source at work? The very existence of a young surface in that frozen wasteland is a direct challenge to our models, a quiet signal that we still do not understand how worlds age in the dark. That young, unblemished surface holds a specific chemical secret, one that whispers of hidden reservoirs or ancient origins. The presence of methane ice on Eris is a profound anomaly in itself. Methane is a highly volatile substance. At the extreme cold and vacuum of the Kuiper Belt, it should not stick around for billions of years. Like a block of dry ice on a warm day, it should slowly but steadily sublimate, turning directly from a solid into a gas and drifting off into space. Yet our telescopes clearly see its spectral signature imprinted on Eris's bright shell. This means the methane we detect is either being continuously replenished or it was deposited so recently on an astronomical timescale that it hasn't had time to vanish. So, where is it coming from? The first possibility points inward toward the dwarf planet's hidden interior. Methane could be trapped within Eris's icy mantle or even dissolved in a potential subsurface ocean. If internal heat from radioactive decay or tidal forces creates even the faintest geological activity, this methane could be slowly released. It would seep upward through cracks and fissures, outgassing onto the surface as a frosty breath. This would make Eris an active world, with a slow but steady supply refreshing the methane that is constantly being lost to space. The process would be invisible to us, a silent exhalation over millennia, but it would explain the persistence of such a fleeting compound. A second, completely different explanation involves the harsh environment of space itself. Eris's surface is bombarded by cosmic rays and the solar wind, a relentless rain of high-energy particles. This radiation can act like a tiny laboratory, breaking apart the molecules of other ices already present, like water or carbon monoxide. These shattered fragments can then recombine in the bitter cold to form new, more complex molecules, including methane. This process, called radiolysis, could be manufacturing methane right on the surface, using the raw materials at hand. It would be a surface-level chemical factory, powered by the violence of space, constantly producing a fresh supply to replace what sublimates away. The third possibility reaches back to the very beginning of the solar system. Perhaps Eris did not form in the same region as other Kuiper Belt objects. It might have originated in an even colder, more distant part of the primordial cloud, a nursery so frigid that methane could freeze solid and remain stable. If Eris then migrated inward to its current orbit, it could have carried with it a deep, primordial layer of methane ice, a pristine relic from the solar system's birth, protected for eons beneath an insulating blanket of other ices. In this scenario, the methane we see isn't being made or released. It is simply being uncovered, like an archaeological layer exposed by that slow resurfacing process. Each answer paints a dramatically different portrait of this distant world. Is it a geologically active body breathing out ancient gases? Is it a passive laboratory where space itself writes chemistry on its surface? Or is it a perfectly preserved fossil, a time capsule holding ices that have vanished from everywhere else? The methane is a clue, but one that points in multiple directions at once, leaving us to wonder what other secrets are frozen into that gleaming, enigmatic surface. The methane clinging to Eris's surface exists within an environment of profound and puzzling cold. Even for its vast distance from the Sun, Eris registers as exceptionally frigid. Observations peg its average surface temperature at a bone-chilling -405 degrees Fahrenheit, only about 30 degrees above absolute zero. This is notably colder than Pluto, which orbits closer to the Sun, but the difference is more extreme than simple distance can explain. The key lies in a property called thermal inertia. Think of thermal inertia as a measure of a surface's stubbornness to change temperature. A material with high thermal inertia, like dark rock or ocean water, absorbs heat slowly and releases it slowly, maintaining a more stable temperature. A material with low thermal inertia, like fine powder or fresh snow, heats up and cools down incredibly fast. Eris exhibits remarkably low thermal inertia. This means that when the feeble sunlight touches its surface, the heat does not penetrate or linger. It is reflected almost instantly back into space, and when that patch of surface rotates into darkness, it plunges back into the deep freeze with startling speed. This behavior strongly suggests the surface is not a solid slab of ice, but a porous, fluffy layer, like a cosmic frost or a blanket of fine, icy powder. It would be like walking on the driest, coldest snow imaginable, a material that offers no thermal memory from one moment to the next. This creates a fascinating contradiction with the idea of geological activity. How can a world with a potentially warm, differentiated interior and a surface being constantly renewed also be covered in a layer of insulating fluff that acts like a perfect thermal mirror? One possibility is that we are seeing two different layers. The brilliant, high-albedo surface could indeed be a delicate frost, just microns thick, sitting atop a much more solid and potentially active icy crust. This frost would dictate the thermal properties we measure from afar, while the real geological drama unfolds safely insulated beneath it. Another, more intriguing idea involves stark contrasts we cannot see. Our telescopic view of Eris blends its entire surface into a single pixel of light and temperature. What if its terrain is a patchwork? Vast bright plains of this cold, fluffy frost could dominate, giving us the low average temperature and thermal inertia. But hidden within could be smaller, darker regions, exposed patches of older, more solid ice, or even the vents of cryovolcanoes. These darker areas would absorb more sunlight, becoming localized warm spots, perhaps only a few degrees warmer, but enough to drive subtle processes. These could be the engines of resurfacing, the places where ices sublimate to later fall as frost elsewhere. The surface temperature puzzle forces us to see Eris not as a uniform billiard ball, but as a complex world of extremes where a blanket of eternal frost might conceal whispers of warmth from below. The profound, cold, and puzzling surface of Eris forces us to look beyond this single world to the strange family it was forced to join. Eris is not alone in the distant dark. It belongs to a category with Pluto, Haumea, and Makemake, the dwarf planets of the Kuiper Belt. Yet, when we place them side by side, Eris stands apart as a stark outlier, a misfit among misfits. This comparative mystery asks whether Eris is a true sibling or a foundling from a different part of the cosmic nursery. Take density, for instance. Pluto, for all its complexity, has a density that suggests a roughly 50-50 mix of rock and ice. Haumea, shaped like a flattened football, is even denser, implying a rockier interior. But Eris surpasses them all, its high density pointing to a disproportionately large rocky core. Then there is the matter of that brilliant shine. Pluto's surface is a complex tapestry of dark, red-tholin-stained plains and bright, icy glaciers. Makemake is also very bright, but Haumea presents a different story, with crystalline water ice giving it a high albedo but a mottled, reddish appearance. Eris outshines them all with its uniform, mirror-like reflectivity. Even their moons tell different tales. Pluto has a system of 5 moons, including the massive Charon. Haumea has 2 small, fast-orbiting moons. Makemake has 1 tiny, faint companion. Eris has Dysnomia, a moon so large relative to its parent that it echoes the Earth-Moon system, born from a colossal impact. These are not minor variations, they are fundamental differences in structure, history, and surface activity. So, what does this mean? One compelling idea is that Eris represents a different class of object altogether. Perhaps it did not form in the same region of the primordial Kuiper Belt as Pluto and the others. It might have originated much closer to the giant planets, in a denser, warmer part of the early solar system where more rock could accumulate into its core. Then, through the gravitational chaos of planetary migration, it was violently scattered outward to its present lonely orbit. In this scenario, Eris is an immigrant, a world with a different birthplace and composition that now resides among, but is not truly of, the classical Kuiper Belt objects. The alternative is that Eris is simply the extreme end of a spectrum. The Kuiper Belt may not be a uniform population of similar ice-rock mixtures. Instead, it could be a diverse collection of worlds that formed across a wide range of distances and conditions, with Eris being the most rock-dominated, most thermally evolved member we have found so far. Its high density and potential for internal activity might not be unique, just the most pronounced. This would imply that other distant dwarf planets, ones we assume are simple, inert ice balls, could harbor similar hidden complexities, dense cores, subsurface oceans, or active resurfacing waiting to be discovered. This comparative mystery transforms our search. If Eris's secrets are unique, it becomes a singular cosmic artifact, a Rosetta Stone for understanding planetary scattering. But if its mysteries are just the most visible clues, then every faint point of light in the Kuiper Belt becomes a potential world of hidden fire and ice, forcing us to wonder what other extremes are waiting in the dark, silently defying our expectations. That dense, rocky core at the heart of Eris whispers of a possibility almost too strange to believe. Beneath its brilliant, frozen crust, could there be a hidden sea? The concept of a subsurface ocean on a world so distant from the sun challenges everything we assume about where life might exist. The evidence is circumstantial but profoundly compelling. It begins with that high density which tells us Eris is not a uniform ball of ice. A significant portion of its interior is rock and metal, and within that rocky core, radioactive elements like uranium, thorium, and potassium are slowly decaying. This process, called radiogenic heating, generates a faint, persistent warmth, a tiny nuclear furnace that has been burning for billions of years. On its own, this heat would be insufficient to melt ice at the surface. But deep underground, insulated by an overlying shell of ice hundreds of miles thick, that gentle warmth could be trapped. It creates a thermal blanket, raising the temperature just enough that, in a specific layer between the cold crust and the warm core, conditions might allow ice to transition into something else, liquid water. But pure water would freeze solid at these pressures and temperatures. This is where chemistry performs its magic. Within the primordial mix that formed Eris, there were likely other compounds that act as powerful antifreeze. Ammonia is a prime candidate. Mixed with water, it can lower the freezing point dramatically by over 100 degrees Celsius. Salts, like those found in Earth's oceans or on Jupiter's moon Europa, could have a similar effect. If Eris's mantle contains even a small percentage of these antifreezes, the boundary between solid and liquid becomes blurred. Deep below the surface, the ice could become a slushy, briny mixture, and eventually a global ocean of dark, salty water, completely isolated from the universe above. This ocean would be unlike any on Earth. It would have no sunlight, no atmosphere, and crushing pressure. It would be a world of perpetual midnight, its only energy the faint geothermal warmth from the core and the chemical potential of the minerals dissolved within it. The implications for astrobiology are staggering. For decades, the habitable zone has been defined as the orbital region around a star where a planet can maintain liquid water on its surface. Eris shatters that narrow definition. If it holds an ocean, it proves that liquid water, the essential ingredient for life as we know it, can exist far outside the traditional habitable zone, powered not by starlight, but by the internal heat of a world itself. This expands the potential abodes for life across the entire solar system and the galaxy. Such a subsurface ocean on Eris would be a cryptic habitat, a locked vault of liquid in the deep freeze. Life there, if it exists, would face extreme challenges: no photosynthesis, scarce energy, and isolation for eons. Yet on Earth, we find thriving ecosystems in the most inhospitable places, around deep-sea hydrothermal vents, buried in Antarctic ice, and in rocks miles underground. These extremophiles survive on chemical energy, a process called chemosynthesis. A similar story could unfold in the dark abyss of Eris. The rocky core, interacting with the water, could provide the necessary chemical disequilibrium. Hydrothermal vents, though likely cold and slow by Earth standards, might seep minerals into the water, offering a fuel source for microbial life. This would not be a world of complex creatures, but a potential refuge for simple, hardy organisms, a biosphere existing in total isolation, its evolution driven by geology and chemistry alone. Eris, therefore, transforms from a frozen curiosity into a cryptic candidate for one of the most profound discoveries imaginable. That life is not a fluke of Earth, but a potential tenant of any world that can cradle liquid water, no matter how dark or distant. Even its brilliant white facade may not be perfectly uniform. Beyond the overarching mystery of its incredible shine lies a more subtle puzzle: the potential for color variations across the surface of Eris. From our unimaginable distance, the dwarf planet appears as a single, dazzling pixel of light. Yet within that pixel, some of the faintest, lowest resolution data hints at something more complex. The color is not perfectly consistent. There are subtle shifts, whispers of darker reds or perhaps slightly bluer tones in different observations. These hints suggest Eris is not a featureless billiard ball, but a world with its own geography, its own hidden continents of ice and stain. So, what could create these subtle patches on a world so cold and bright? One possibility lies in the texture of the ice itself. The size of the ice grains on the surface can dramatically affect how light reflects. A smooth plain of fine, powdery frost will scatter light differently than a region of coarse, crystalline ice blocks. A patch where the ice grains are larger and more compact might appear slightly darker or have a different hue than an area covered in brilliant, fresh snowfall. Another explanation points back to the contaminant we suspect is there, tholins. These reddish-brown organic gunks are created when methane and other simple ices are zapped by radiation. It is possible that this tholin dust is not evenly distributed. Prevailing winds from a transient atmosphere, however faint, could have swept the dark material into specific basins or coated the slopes of certain terrain features over millions of years. Imagine dark, rusty streaks gathering in the lee of icy mountains, or vast plains that are slightly more pristine and white than others. A third, more radical idea is the exposure of bedrock. If Eris's resurfacing processes are not global and instantaneous, there could be regions where the icy conveyor belt has stalled. In these places, the bright overburden might have been stripped away by sublimation or impacts, revealing the darker, rocky material beneath the ice shell. This would be like a scab on the world's surface, a window directly into its dense, rocky interior. The frustrating truth is we simply cannot know. Mapping these variations is currently impossible. Our most powerful telescopes, like Hubble, can barely resolve Eris as anything more than a point of light. To chart its surface, to see if it has a heart-shaped plain like Pluto's Tombaugh Regio, or a dark equatorial belt like on Makemake, we need a spacecraft to visit. We are left to wonder if the smooth, bright world we imagine is actually a tapestry of different terrains. Does it have vast, gleaming glaciers of nitrogen ice flowing into basins of water ice bedrock? Are there impact craters whose floors are pools of shadowy, complex organics? Could there be cryovolcanic domes, their fresh, white flows standing out against older, stained terrain? every other comparable world we've seen up close has surprised us with its complexity. Pluto was a revelation of diversity with mountains, plains, glaciers, and a hazy atmosphere. There is no reason to believe Eris, with all its other extreme properties, would be any simpler. Its potential color variations are a silent promise that beneath that single point of light in our telescopes lies an entire unexplored world, waiting for its first visitor to reveal its true face. Even the length of a day on Eris is a subject of fierce debate. We do not know how fast this distant world spins. For most planets and even many asteroids, determining the rotation period is straightforward. Astronomers measure the object's light curve, the regular rise and fall in brightness as different sides, with their varying terrains and reflectivity, rotate into view. A mountain range or a dark patch will reflect less light than a smooth, bright plane, creating a recognizable pulse in the data. With Eris, this simple method fails spectacularly. Its light curve is maddeningly flat. There is no clear, repeating pattern of brightening and dimming. This suggests one of two extraordinary possibilities, each with profound implications. The first is that Eris is tidally locked to its moon Dysnomia, just as our moon is locked to Earth. In this scenario, Eris's rotation period would exactly match the orbital period of Dysnomia, about 15.8 Earth days. From the surface, Dysnomia would hang motionless in the sky, but this lock would not be simple. Because of Eris's elongated orbit and Dysnomia's own path, the lock might be a complex spin-orbit resonance, a subtle dance where the rotation speeds up and slows down slightly over the long orbital cycle. The second possibility is even stranger. Eris might be rotating very quickly, completing a full turn in just a few hours. If its surface is as perfectly uniform and smooth as it appears from our distant vantage point, with no significant dark or bright features to create a light curve signature, we would detect no pulse in its brightness regardless of how fast it spins. A world with a perfectly homogeneous, mirror-like shell would betray no daily rhythm to our telescopes. Each answer tells a radically different story about its history. A slow, locked rotation points directly to the colossal impact that created Dysnomia. That ancient collision would have sent Eris into a violent, chaotic spin. Over the eons, the gravitational tug of war with its massive moon would have acted as a brake, gradually slowing that spin until they reached their current synchronized state. The time it took to achieve this lock is a secret clock, telling us about the internal flexibility of both bodies. If they locked quickly, it means their interiors were deformable, able to flex under tidal forces, again hinting at layered structures and potential subsurface slush. A fast rotation, on the other hand, would be a shocking revelation. It would mean the tidal braking from Dysnomia was surprisingly ineffective, perhaps because the moon's orbit is more circular than we think, or because Eris's interior is more rigid and unyielding than our models predict. There is another, more exotic break that could have slowed Eris's spin, a ghost from its past. If Eris once possessed a much more substantial atmosphere during the warmer periods of its extreme orbit, that envelope of gas could have created drag against the surface. Over millions of years, even a thin atmosphere can act like a gentle hand on a spinning top, gradually slowing the world's rotation through a process called atmospheric tidal friction. A slow rotation today could be the fossilized imprint of an ancient, lost sky. Then there is the question of tilt. Does Eris spin upright, or is it knocked over on its side like Uranus? Its axial tilt, the angle between its rotation axis and its orbital plane, is another complete unknown. A severe tilt could be a direct scar from the Dysnomia-forming impact, a permanent record of the angle of that catastrophic blow. It would also create extreme seasonal contrasts on a world that already experiences wild temperature swings, with one hemisphere facing the sun for decades while the other languishes in a century-long night, potentially driving even more dramatic volatile transport across its surface. Without knowing the length of its day or the tilt of its axis, we cannot truly model its climate, its weather, or the forces that shape its landscape. The silent spin of Eris holds the key to its most violent moment and its long, quiet evolution since. The silent spin of Eris hints at a violent past, but its very substance tells an even deeper story. Its high mass is a fundamental puzzle. For its physical size, Eris contains far more rock and metal than we would predict for a typical denizen of the Kuiper Belt. This isn't just a small difference, it's a structural anomaly that forces us to question where and how this world was built. The classical objects out there are thought to be primordial leftovers, icy planetesimals that never grew large enough to become planets. They are mixtures of rock and ice, but Eris seems to have gotten the recipe wrong, adding an extra scoop of stone to the mix. So how did it become so dense? One compelling origin story begins much closer to the Sun. In the chaotic early solar system, the region around the giant planets was a dense soup of material. Here, closer to the heat of the young Sun, volatile ices were less stable, so the building blocks that coalesced were naturally richer in rock and metal. Imagine a construction site where bricks are more plentiful than snow. If Eris began its life in this rockier neighborhood, it would have formed with a disproportionately large core from the start. Then, during the grand migration of the giant planets, the gravitational turmoil could have acted like a cosmic catapult, flinging this dense, half-formed world outward into the frozen depths of the scattered disk. In this scenario, Eris is an immigrant, a refugee from the inner solar system now living in the icy outskirts, its rocky heart a permanent reminder of a warmer birthplace. Another possibility is that Eris is not an immigrant but a glutton. It may have formed right where it is, but through a series of extraordinary mergers. While most Kuiper Belt objects grew by gently accumulating pebbles of ice and dust, Eris might have been the victor in a series of giant impacts. Think of it not as a snowball gently rolling through a field of powder, but as a snowball that collided with and absorbed other large snowballs again and again. Each colossal merger would have added more mass, potentially allowing it to gravitationally attract and hold onto more of the heavier rocky material that might otherwise have sunk toward the Sun. Through this process of runaway accretion, Eris could have become the heavyweight champion of its local region, a product of exceptional violence and chance that left it more massive than its peers. There is a third, more destructive explanation. What if Eris was not always this dense? What if it started as a larger, more typical icy body, but a catastrophic event stripped away its outer layers? The colossal impact that created its moon Dysnomia was undoubtedly violent, but it may have been even more transformative than we realize. The energy of that collision would have been staggering, vaporizing immense quantities of surface and mantle ice. If the impact was glancing and powerful enough, it could have blown a significant portion of Eris's original icy mantle clean off into space, leaving behind a world that is essentially a large rocky core with a much thinner, recondensed icy shell. In this brutal scenario, Eris's high density is not a sign of how much it gained, but of how much it lost. Its mass is a scar, the remnant core of a larger, icier world that was brutally sculpted by a single shattering blow. Each of these origins paints a different cosmic biography. Is Eris a traveler, a glutton, or a survivor? Its silent, heavy presence in the dark is a riddle written in rock and ice, a single data point that challenges our simplest stories of how worlds are made and where they belong. The heavy rock at its core is not the only clue to its past, for the very ice on its surface holds a chemical enigma. Among the spectral whispers we detect from Eris, one signature remains frustratingly elusive, the clear fingerprint of solid nitrogen. This is a mystery of absence, a missing piece that complicates our entire picture. We strongly suspect nitrogen is there. It dominates the surface of Pluto and is common on other large Kuiper Belt objects. On Eris, the overall brightness and temperature profile would be perfectly explained by a coating of nitrogen frost. Yet, our telescopes have struggled to lock onto its definitive spectral signal. This isn't a simple yes or no, it is a game of cosmic hide-and-seek played across 4 billion miles. The challenge is one of physics and distance. Nitrogen ice, especially when cold and pure, has a very subtle spectral signature. Its molecules do not absorb or reflect light in dramatic, easy-to-spot ways like methane or water ice. Detecting it is like trying to identify a specific type of clear glass by looking at a distant window with a pair of binoculars on a foggy day. The faint light we receive from Eris is already stretched and diluted. Any nitrogen signal is easily washed out by the stronger signatures of methane or blurred by the presence of complex tholins. It might be there, mixed intimately with other ices, its quiet voice drowned out by louder chemical neighbors. So we are left with a pressing question. If nitrogen is present, where did it come from? One origin is primordial. Nitrogen, in the form of ammonia or molecular nitrogen ice, could have been a fundamental building block from the solar system's birth cloud, incorporated directly into Eris as it formed. This would make it a native substance, a relic frozen in place for eons. The alternative is that it is a manufactured product. The relentless radiation bombarding Eris's surface could be acting as a cosmic alchemist. High-energy particles could be breaking down ammonia, ice, or other nitrogen-bearing compounds, liberating the nitrogen to recombine and freeze as a new surface frost. This would mean the nitrogen we might see isn't ancient but contemporary, a testament to the ongoing chemical processing on this distant world. The stakes of this detection are surprisingly high. Nitrogen is not just another ice, it is a master key. Its presence and form dictate the potential for atmosphere. Nitrogen is highly volatile, meaning it sublimates easily. If Eris has solid nitrogen on its surface, then during the warmer parts of its extreme orbit, that nitrogen could sublimate to create a temporary, tenuous atmosphere, however thin. This would be the engine for the resurfacing cycle we suspect, where nitrogen gas carries away dark dust and then snows back down as bright frost. Furthermore, the physical state of the nitrogen tells a story. Is it in large, crystalline grains or a fine, amorphous frost? Is it pure or locked in a molecular cage with other ices? Each form points to different temperature histories and surface processes. The elusive spectral signature of nitrogen ice is therefore more than a technical hurdle for astronomers. It is a direct line to understanding whether Eris breathes, whether it has seasons, and what raw materials from the dawn of the solar system still linger on its gleaming, frozen skin. The chemical whispers from its surface are echoes of a much older story, written not in ice but in motion. To understand Eris, we must rewind the cosmic clock and watch its violent journey unfold. Its orbit is a screaming anomaly, a stretched and tilted loop that stands out even among the strange paths of the Kuiper Belt. How did it get there? The answer lies in the solar system's chaotic adolescence, a time of gravitational upheaval we can only reconstruct with powerful computer simulations. These digital time machines let us play out millions of possible histories, searching for the one that leads to the lonely orbit we see today. The leading suspect in this celestial crime has always been Neptune. In the most widely accepted model, the giant planets migrated outward in their youth, their immense gravity acting like a tidal wave through the sea of icy debris around them. A primordial Eris peacefully orbiting closer to the Sun would have been caught in this chaos. A series of close gravitational encounters with Neptune could have acted like a slingshot, each pass flinging it farther out, pumping its orbit into the extreme ellipse we observe and tilting it high above the planetary plane. This would make Eris a classic member of the scattered disk, a population of icy objects literally scattered by Neptune's influence. It is the largest known member of this exiled family, a king of the refugees. But some simulations suggest this story might be too neat. Eris's orbit is so exceptionally elongated and inclined that achieving it through Neptune's influence alone is statistically challenging. It pushes the limits of the model. This has led scientists to consider an even more distant point of origin. Could Eris have begun its life not in the Kuiper Belt at all, but in the inner Oort cloud? This is a hypothesized spherical shell of icy bodies far beyond the scattered disk, a reservoir of comets so distant they are only loosely bound to the Sun. A gravitational nudge from a passing star in the Sun's long history, or the gentle pull from the galactic tide itself, might have dislodged a young Eris from this deep freeze, sending it tumbling inward until it was captured into its current orbit by Neptune's gravity. This would make it a true interstellar immigrant on a scale we rarely consider. Each potential history imprints different characteristics on the world we see. If Eris was violently scattered by Neptune, that process would have been incredibly energetic. The gravitational tugs would have heated its interior through tidal friction, potentially melting its icy mantle and kick-starting the differentiation that gave it such a dense core. That heat could have lasted for hundreds of millions of years, driving early geological activity and perhaps even giving a subsurface ocean its initial warmth. If, however, it fell gently inward from the Oort cloud, its interior might have remained colder and more primordial, its structure less processed. Its surface chemistry could reflect a different blend of ices from a colder natal region. Its very density might be a clue to its birthplace. The puzzle of its dynamical history is therefore not just about its path. It is about using that path as a forensic tool to peer inside the world itself. The orbit is a scar, and by reading its shape, we can deduce the nature of the ancient violence that created it. Every simulation run is an attempt to answer a single, profound question. Is Eris's strange orbit the signature of a known giant planet's past mischief, or is it a clue pointing to an even more distant and mysterious chapter in the Sun's life, a time when other stars passed close by and stirred the depths of our own celestial backyard? Dysnomia is a giant companion, but is it truly alone? The possibility of additional, unseen moons orbiting Eris is a quiet but persistent question. Our view from Earth is profoundly limited. Spotting a moon like Dysnomia was a monumental feat, and it is large and relatively close to its parent. Any smaller, fainter moons hiding farther out in the darkness would be virtually invisible to our current telescopes. They could be mere flecks of ice just a few miles across, lost in the glare of Eris's brilliant disk, or orbiting at such a great distance that our observations have simply missed them in the sparse data. The search for these hidden satellites is not just a census, it is a direct investigation into Eris's most violent and formative moments. Moons are created through three fundamental processes, and each would leave a different signature on the system we see today. The first and most dramatic is the collision that likely birthed Dysnomia. A giant impact doesn't just create one large moon. It hurls a colossal cloud of debris into orbit, a swirling disk of shattered rock and ice. While much of that material would quickly coalesce into the primary moon, some could clump together into smaller secondary satellites or remain as a faint, dusty ring for a time. If Eris has a family of smaller moons, they would be direct fragments from that ancient catastrophe, siblings to Dysnomia sharing a common origin. The second possibility is capture. As Eris journeyed through the crowded early Kuiper Belt, its gravity could have snared a passing, smaller object, pulling it into a stable orbit. This would be a moon with a completely different composition and history, a stranger adopted into the system. The third, more orderly idea is co-formation, where Eris and multiple moons condense together from the same swirling cloud of primordial material, a miniature solar system in its own right. Each scenario imprints different clues. The presence of even one tiny, additional moon would be a revelation. Its orbit would act as a delicate probe of Eris's gravitational field. By tracking the subtle wobbles and tugs on these smaller bodies, Astronomers could map the distribution of mass inside Eris with incredible precision, confirming the size of its rocky core and the thickness of its icy mantle far better than Dysnomia's orbit alone allows. The orbits of multiple moons would also tell the story of their birth. Moons formed from the same debris disk would likely orbit in the same plane like planets around the Sun. A captured moon, however, could have a wildly tilted or even retrograde orbit, going the wrong way compared to Eris's spin. Its very path would be a confession of its foreign origins. Yet, the absence of other moons is equally meaningful. If deep, sensitive searches eventually confirm that Eris and Dysnomia are a perfect, clean binary, it suggests something profound about that ancient impact. It must have been a remarkably efficient event. The debris disk was either mostly absorbed by Dysnomia or quickly dissipated, leaving no smaller siblings behind. This would point to a specific type of collision, perhaps a more direct central hit rather than a glancing blow, that created a simple two-body system from the chaos. For now, the space around Eris is a realm of shadows and unanswered questions. We have seen only one dancer in what could be a wider ballet. Until a spacecraft visits or our telescopes peer deeper, we must wonder if Dysnomia keeps its lonely vigil, or if it shares its silent sky with other, fainter companions, unseen sentinels from a time of cosmic violence. Even the space around Eris may not be empty. Beyond the physical world of rock and ice lies a more intangible mystery, the question of its magnetic personality. Does this distant dwarf planet possess a magnetic field? For a world so cold and remote, the idea seems far-fetched, but the clues hidden within its structure make it a tantalizing possibility. The recipe for a planetary magnetic field requires three key ingredients: a fluid, electrically conductive layer in motion, a source of energy to drive that motion, and the planet's own rotation. On Earth, our magnetic field is generated by the churning of molten iron in the outer core, a self-sustaining dynamo powered by heat and our planet's spin. For Eris, the potential conductive fluid isn't molten metal, but a subsurface ocean. If a global sea of salty, mineral-rich water exists beneath the ice, and if that ocean is in contact with a hot, rocky core, the conditions for a dynamo could be met. The heat from the core would drive convection in the ocean, the salt makes the water electrically conductive, and the slow rotation of Eris, however long its day may be, could organize that motion into a coherent magnetic field. It would be a ghostly, weak field by Earth standards, but it could exist. The implications of such a magnetic bubble are profound. As the solar wind, that relentless stream of charged particles from the Sun, travels across the billions of miles to the edge of the system, it would eventually encounter Eris. A magnetosphere would act as a shield, deflecting these particles around the world. Without it, the solar wind would strike the surface directly, bombarding the ices and contributing to the space weathering that creates dark tholins. A magnetic field could therefore be a key player in preserving that brilliant, reflective surface by providing a protective barrier against this constant erosion. More spectacularly, a magnetosphere could create auroras. On Earth, charged particles channeled by our magnetic field collide with atmospheric gases to paint the sky with the northern and southern lights. Eris has no substantial atmosphere, but if it possesses even a whisper-thin envelope of gas during its orbital warm periods, a magnetic field could funnel solar particles into it, potentially sparking faint, ethereal glows near its poles. These would be auroras unseen by any eye, dancing in absolute silence over a frozen landscape, yet all of this remains in the realm of pure speculation. Our instruments cannot detect a magnetic field from this distance. We have no way to measure the electrical conductivity of a hypothetical ocean or the precise rotation rate needed to twist it into a dynamo. Eris's electromagnetic character is a complete enigma, a hidden layer of its identity that could fundamentally alter our understanding of its environment and its history. The presence or absence of this invisible force field would tell us if Eris is an active world with a churning, salty heart, or a passively frozen body where even the solar wind meets no resistance. It is a mystery locked inside a mystery, waiting for a visitor to bring a compass to the edge of the dark. The potential for a magnetic field hints at a world with a churning interior, but the true chemical drama of Eris may be playing out right on its surface, written in a substance the color of rust. Tholins are not a single compound, but a family of complex organic polymers, a sticky, reddish-brown gunk that forms when simple ices like methane and nitrogen are bombarded by ultraviolet light or cosmic rays. They are the cosmic equivalent of tar, created by radiation baking basic ingredients into more complicated organic goo. Their suspected presence on Eris is not just a detail about its color, it is a profound astrochemical mystery. If tholins coat parts of that brilliant surface, they are a permanent record of relentless photochemistry, a process that has been running non-stop for billions of years. Imagine the feeble sunlight over astronomical timescales, acting like a slow, weak ultraviolet lamp in a cosmic kitchen. It steadily zaps molecules of methane ice, breaking their atomic bonds. These shattered fragments, unstable and eager to reconnect, collide and stick together in the bitter cold, forming longer and more complex chains. Over millions of years, this relentless, silent irradiation can transform a pristine layer of simple ice into a veneer of complex organic material. This process turns Eris into something far more significant than a frozen rock. It becomes a natural laboratory, a deep freeze archive where the universe is conducting its own experiments in probiotic chemistry. Probiotic chemistry refers to the natural formation of the organic compounds that are the necessary precursors for life as we understand it. It is the set of steps that might turn inert matter into the building blocks of proteins, membranes, and genetic material. The tholins on Eris are not alive, but they represent a critical intermediate stage. They show that in the most inhospitable environments, with just simple ices and energy from starlight, the universe has a tendency to build complexity. The reddish patches we infer could be vast fields of this organic material, a frozen library of chemical experiments that have been running since the solar system was young. This raises a staggering possibility. Could Eris' surface be a museum preserving the very types of compounds that, on a warmer, wetter world like early Earth, were delivered by comets and asteroids to seed our oceans with life's raw materials? We often think of comets as the delivery vehicles for water and organics, but a dwarf planet like Eris represents the source factory. Its tholins are a snapshot of the chemical evolution that happens in the dark, cold reaches of space, a process that may be universal. Every icy body in the outer solar system is likely undergoing some version of this radiation-driven chemistry. On Eris, with its potential for resurfacing and renewal, the story is particularly dynamic. Fresh methane ice brought to the surface by cryovolcanism or frost migration would provide new raw material. The radiation would then begin its slow work anew, creating layers of organics that are then perhaps buried by fresh ice, only to be exhumed later. The surface could be a layered cake of chemical history, with strata recording different epochs of irradiation and renewal. This transforms the mystery of Eris color from one of mere appearance to one of profound astrobiological significance. It asks us to consider whether the path to life is not a rare accident, but a chemical imperative written into the fabric of icy worlds. Eris, in its silent, frozen state, may be holding a recipe book we are only beginning to read, its pages stained red with the complex, non-living ink of creation. That slow chemistry unfolding on its surface requires energy, but the true engine of any world lies deeper within. To solve the riddles of Eris, we must confront a fundamental thermodynamic mystery, the source of its internal heat. What is the heat budget of this distant world, and is it enough to power the activity we suspect? The numbers at first glance seem impossibly small. The sunlight Eris receives is negligible, a faint whisper that barely warms its brilliant frost. The primary internal source should be the decay of long-lived radioactive isotopes like uranium, thorium, and potassium, trapped within its dense rocky core. For a world of Eris's size, this radiogenic heating would have been strong in its youth, but over 4.5 billion years, that output has dwindled to a faint, steady glow. By all standard models, this residual warmth should be utterly insufficient to maintain a subsurface ocean or drive the global resurfacing that keeps its face so young and bright. The math simply does not add up, leaving a glaring energy deficit. This forces us to consider other, more exotic furnaces that might still be burning in the dark. One compelling candidate is tidal heating. Eris is locked in a gravitational embrace with its large moon, Dysnomia. As the two bodies orbit each other on their elongated path around the Sun, the gravitational pull between them flexes and stretches their interiors. This constant, rhythmic deformation generates friction, and friction produces heat. We see this process in dramatic action within the volcanic moons of Jupiter, like Io. For Eris, the effect would be far more subtle, a slow, steady kneading of its icy mantle over eons. The critical question is whether this tidal input is significant enough to bridge the energy gap. The answer depends on details we lack: the precise rigidity of Eris's interior, the exact shape of Dysnomia's orbit, and the history of their orbital evolution. If their dance has resonances, periods where their gravitational tugs aligned in just the right way, tidal heating could have experienced brief but powerful surges, injecting pulses of warmth that might still be echoing through its structure today. Beyond tides, we must consider the physics of the materials themselves. The interior of Eris is not a simple, static stack of rock and ice. As the world slowly cools and the pressure changes with depth, the very phases of its constituent materials can shift. Water ice under immense pressure can crystallize into exotic forms like Ice 6 or Ice 7, denser structures that release latent heat as they form. Similarly, the rocky core might undergo phase changes in its silicate minerals. Each of these transitions, happening over geological timescales, acts as a tiny battery, releasing stored energy as heat. It is a slow-motion exothermic reaction built into the fabric of the world. There is also the lingering heat from its violent formation and the colossal impact that created Dysnomia. That single event would have delivered an unimaginable surge of energy, essentially flash cooking a significant portion of the mantle. While most of that heat would have radiated into space quickly, some could have been trapped deep within, a buried ember taking billions of years to cool. The combination of these sources, radiogenic decay, tidal flexing, phase changes, and impact heat, might create a complex thermal history. It is possible that Eris experiences episodic warming, long periods of quiet cooling punctuated by brief phases of activity when different heat sources briefly align. This could explain a young surface without requiring a constant, powerful engine, a world that wakes up for a geological moment, refreshes its face, and then returns to a long slumber. The foundational puzzle of its heat flow is therefore not just about accounting for watts of energy. It is about determining whether Eris is a dying cinder, its internal fires nearly extinct, or a world with a hidden, rhythmic pulse, still capable of surprising us with the slow, majestic force of its hidden warmth. But perhaps Eris is not the only exile. To fully grasp its story, we must look beyond it to an even more distant and solitary wanderer, an object named Sedna. While Eris roams the scattered disk, its orbit still loosely influenced by Neptune, Sedna exists in a realm of true isolation. Its path is staggering, a 12,000-year loop that takes it from 76 times Earth's distance from the Sun out to a mind-numbing 936 times that distance. At its farthest, Sedna is a month's travel away from the Sun at light speed. More crucially, its orbit is detached, meaning it never comes close enough to Neptune for the ice giant's gravity to have sculpted its path. It is an island in the gravitational sea, forever cut off. This presents a profound comparative mystery. How can two extreme worlds, Eris and Sedna, both exist in our solar system, yet follow such different rules? Their properties offer stark contrasts. Sedna is redder than Eris, its surface darkened by eons of unshielded cosmic radiation. It is likely smaller and less massive, a lonely, dark sentinel. Eris is brilliant, dense, and accompanied by a large moon. They seem like different species, yet their very extremeness forces a haunting question. Could they, despite their differences, be products of the same ancient catastrophe? The leading theory for Sedna's detached orbit involves a dramatic early solar system event. One compelling idea is the close passage of another star in the Sun's infancy, a stellar sibling from the same birth cluster. The gravity of this passing star could have plucked Sedna from the inner Oort cloud and flung it into its current, tightly bound, yet incredibly distant orbit. If this happened, could it also have affected Eris? Perhaps Eris was not scattered by Neptune alone, but received a gravitational kick from this same stellar visitor, helping to pump up its orbit's eccentricity and tilt. In this shared story, both worlds become refugees from the same stellar near miss, their paths frozen records of a time when another sun briefly shared our sky. The other prime suspect is the hypothetical planet 9, a massive world thought to be orbiting hundreds of times farther out than Earth. Its persistent gravitational tug could shepherd objects like Sedna into their detached orbits, while also influencing the paths of scattered disk objects like Eris over billions of years. If Planet 9 exists, then Eris and Sedna might not share a direct origin, but they could both be pawns in the same vast, slow-motion gravitational game, their orbits shaped by different moves from the same unseen player. Comparing these two distant dots of light is an exercise in cosmic forensics. Their differences in color, density, and companionship tell us about their individual histories, their unique recipes of rock and ice. But their shared quality of orbital extremeness points to a shared environment of ancient violence. They are both survivors of the solar system's most turbulent era, but they bear different scars. Eris, with its large moon and processed surface, suggests a history of colossal impacts and internal warmth. Sedna, alone and dark, speaks of a colder, quieter existence in the deep freeze. Together, they are bookends, defining the outer limits of where substantial worlds can exist and what forces can put them there. Their silent dance is a clue to a chapter of our history we can only reconstruct from the faint gravitational echoes left in their path. The profound isolation of Sedna and the extreme orbit of Eris define the frontier, but they also highlight our own profound limitation. We are trying to solve a cosmic jigsaw puzzle while missing 99% of the pieces. Every mystery we have explored, from the young surface to the hidden ocean, is filtered through a single, frustrating reality. Our view from Earth is a blurry snapshot from a billion miles away. Ground-based telescopes, even the most powerful ones on mountaintops, must peer through our own turbulent atmosphere, which smears and distorts the faint light from Eris into an indecipherable blob. The Hubble Space Telescope, orbiting above that atmospheric soup, provides our clearest images, but its best view of Eris is still just a single, brilliant pixel of light. We can measure its brightness, estimate its size during a stellar occultation, and break its light into a crude chemical spectrum, but we cannot see its mountains, its craters, or its plains. We are essentially trying to diagnose the health of a patient by listening to their heartbeat from another continent. The fundamental mystery of how we will ever truly know Eris is therefore a practical one, a question of technology, ambition, and patience. The answers will not come from better telescopes on Earth or in orbit. They will come from going there. For decades, mission planners have dreamed of sending a dedicated probe to the distant reaches of the Kuiper Belt, beyond the triumph of new horizons at Pluto. Eris stands as the ultimate prize for such a mission, a world that embodies every unanswered question about the outer solar system. The challenge is immense. Even with a powerful launch and a gravity assist from Jupiter, a spacecraft would take over 2 decades to reach Eris. It would be a journey of a generation, requiring a probe robust enough to survive the cold and radiation of deep space for 25 years or more, only to scream past its target at tens of thousands of miles per hour in a fleeting, hours-long encounter. Yet the scientific payoff would be nothing short of revolutionary. Imagine the first close-up image. That single pixel on our screens would explode into a world. We would see in high definition whether its surface is smooth or scarred, whether dark tholin stains gather in basins or streak across bright glaciers. We would map cryovolcanoes, trace the flow of ancient ice, and count the craters to finally date its surface. A suite of instruments would do in minutes what centuries of Earth-based observation cannot. A thermal mapper would feel the warmth leaking from its interior, pinpointing active regions. A spectrometer would not just hint at methane and nitrogen, but would create a detailed chemical map, showing exactly where different ices reside and how they are mixed. If Eris possesses that ghostly temporary atmosphere, the spacecraft could potentially sample it directly, analyzing its composition and pressure as it flies through. Most profoundly, by carefully tracking the probe's radio signal as Eris's gravity tugs on it, scientists could perform exquisite celestial cartography. They would map the dwarf planet's gravity field in detail, revealing the distribution of mass inside. This one measurement would solve multiple mysteries at once. It would confirm the size and density of the rocky core, measure the thickness of the icy mantle, and potentially detect the sloshing of a subsurface ocean by the way it subtly distorts the gravity signature. Eris would transform from a list of puzzling properties into a known geological entity with an understood internal structure and a documented history. The data would not just be about Eris, it would be a key to the entire Kuiper Belt. By comparing this detailed autopsy of one scattered disk object to what we learned at Pluto, a classical Kuiper Belt object, we would finally understand the true diversity of these icy worlds. We would know if Eris is a unique immigrant or the archetype of a whole class of dense, active dwarfs. The mission would also gaze outward during its long cruise, surveying other faint Kuiper Belt objects along the way, building a census of the dark frontier. While no such mission is currently funded, the will and the concepts exist. It is a question of when, not if. Solving the 25 mysteries of Eris requires accepting a timescale as vast as the distances involved. It means planning a mission that will deliver its answers to scientists who are today in graduate school, or perhaps not even born yet. It is an investment in pure discovery, a message in a bottle we launch into the dark, addressed to the future. The journey to understand Eris is a voyage into the unknown, but its true significance may lie not in what it tells us about ice and rock, but in what it reveals about ourselves. Why does this faint, frozen speck, a world no human eye will ever see directly, hold such a powerful grip on our imagination? Its story is a mirror reflecting our own restless desire to map the edges of our home and define our place within it. Eris did not merely join our solar system, it forced us to redraw the map. For generations, schoolchildren memorized 9 planets, a tidy family portrait. Eris, with its undeniable heft and distant glare, shattered that comfortable arrangement. It was the discovery that broke the model, proving our cosmic neighborhood was far more crowded and complex than we had allowed ourselves to believe. This was not just an addition, it was an intervention. It demanded we create new categories, new language to describe the richness of what actually exists beyond Neptune. In doing so, Eris became a catalyst for a deeper, more nuanced understanding of our own celestial context. Its name, chosen with deliberate irony, proved prophetic. In Greek mythology, Eris was the goddess of strife and discord. She was the one who tossed the golden apple inscribed "For the fairest" into a wedding, sparking the rivalry that led to the Trojan War. Our Eris performed a similar act of cosmic provocation. By its mere existence, it tossed a golden apple of discord into the orderly garden of planetary science. The fierce, public, and passionate debate over Pluto's status was its legacy. Was Pluto a planet? If so, then Eris must be one too, and so would dozens of other worlds. The International Astronomical Union's decision to create the dwarf planet category was a direct response to the dilemma Eris presented. It lived up to its namesake not through malice, but simply by being too significant to ignore. It forced a necessary, if uncomfortable, conversation about what we value in our definitions, reminding us that nature does not always conform to our tidy human-made boxes. Ultimately, Eris represents something far greater than a classification argument. It is a permanent monument to the vast, unexplored frontier that still lies within our own solar system. We send probes to Mars and gaze at the rings of Saturn, yet here, in our own backyard, exists a complete class of worlds about which we know almost nothing. Eris is the ambassador of that frontier, a constant, silent reminder that discovery is never finished. It symbolizes how a single point of light, glimpsed from 4 billion miles away, can ripple through our culture, our textbooks, and our fundamental perspective. It humbles us, proving that even in a time of advanced technology, we are still explorers peering into the dark, forever rewriting the story of home with every new, faint glimmer we find. The journey through 24 specific enigmas brings us to a final, unifying question. What single quality defines Eris? Is it its astonishing density, its mirror-like shine, its wild and lonely orbit, or the profound silence of its companion moon? The answer, after exploring each puzzle, is that no single trait can claim that title. Eris's true uniqueness lies in the impossible combination of all these extremes, a convergence of contradictions that our current models of solar system formation struggle to contain. We have a world that is both incredibly dense and brilliantly reflective, a place that should be a dark, cratered relic yet shows signs of a young, dynamic surface. It is a massive object with a moon born from a cataclysm, following a path so stretched and tilted it seems to defy the very gravity that shaped our planetary neighborhood. Each of these properties in isolation would be remarkable. Together, they create a cosmic anomaly. According to our standard playbook, a dwarf planet in the frozen Kuiper Belt should be a relatively simple mixture of ice and rock, dark from eons of radiation and geologically dead. Eris breaks every rule. Its high density screams of a rocky core more suited to a world that formed closer to the sun. Its dazzling albedo suggests constant renewal, a process requiring energy we cannot fully account for at such a distance. Its extreme orbit hints at a violent past of gravitational scattering, yet its surface appears unblemished by the subsequent eons of impacts that such a journey should invite. This isn't just a world that doesn't fit a category. It is a world that challenges the categories themselves. Eris stands as a permanent testament to the beautiful unpredictability of planetary science. It reminds us that our models are not laws, but stories we tell to make sense of the cosmos, and sometimes the universe writes a story we did not anticipate. The defining characteristic of Eris, therefore, may be its role as a corrective. It is the data point that refuses to be ignored, the outlier that forces us to redraw the graph, to admit that the processes which built our solar system were more creative, more chaotic, and more capable of producing singular wonders than we ever imagined. In its silent, frozen state at the edge of everything, Eris is not merely an object. It is a question mark carved from ice and rock, a perpetual invitation to look deeper and wonder what other impossible combinations are waiting in the dark. This journey through 25 profound mysteries has taken us from a brilliant, gleaming surface to the possibility of a hidden, dark ocean. We have traced the wild orbit of a cosmic refugee and witnessed the silent dance of a moon born from catastrophe. Each puzzle, from the missing craters to the elusive nitrogen, from the enigmatic heat flow to the provocative red tholins, reveals a world that defies simple explanation. Eris is far more than a distant dwarf planet. It is a keystone, a single point of light that holds the potential to unlock our understanding of the entire Kuiper Belt and the violent, migratory history of our solar system. Its contradictions are not flaws but clues, each one a piece of a grander puzzle about how worlds are built, scattered, and transformed in the deep freeze of space. So, as we leave this enigmatic world to its long, silent orbit, we turn the question to you. Which of these 25 mysteries captures your imagination the most? Is it the potential for a subsurface ocean in that profound dark, the young surface that erases its own history, or the orbital tail that might point to an unseen planet 9? Share your thoughts and theories in the comments below. The story of Eris is far from over. It awaits the future mission that will finally bring its secrets into focus. Until then, the mysteries endure. If you enjoyed this deep dive into cosmic puzzles, be sure to subscribe. Our journey through the unexplained wonders of the universe has only